So thank you. So today I'm going to be talking on our work on random walk approach for distributed learning in heterogeneous data systems. I've done this work jointly with Venkat Dasari from the US Army Research Lab and with my PhD advisor, Salim Rouayheb. So in our work, we're considering distributed learning settings where we have a network of nodes and each node in the network is generating some local private data. And the goal is to learn some global model on that fits the distributed data in the network without shipping the data away from its owner. This setting is relevant for many applications. You can think about applications such as federated learning, IoT systems, sensor networks, vehicular networks. So for example, these nodes can be smartphones that are generating their texting data. And the goal is to learn one text prediction model for the entire network. From now on, we're gonna represent the network by a graph. And each node in the graph has its own local data set, which is the set of the data points that are generated or owned by this node. And these data sets tends to be personalized, tends to reflect something about the node style or the node personality. And that's why the local data sets are not identically distributed. They come from different distribution. And this is what we call statistical heterogeneity. And today we're gonna be talking how this is gonna affect the training performance and how we can address this in distributed settings. So what's our goal? Our goal is to learn one global model on the distributed data, but we're gonna do that through implementing a decentralized algorithm. Decentralized algorithm has a lot of advantages. They can be more private. They can address the communication and the storage costs. And also there are advantages if we're looking for a more reliable system. So in decentralized algorithm, we only rely on local communication between the nodes. The server won't be involved in the training. Also, even for the computation, all the aggregation and the computation gonna happen locally at the node site. And what's gonna happen, the decentralized algorithm at the end will output one global model that minimizes what we call the global loss, which is the aggregation of all the local losses in the network, as we see here. And for the technical part, we're gonna have some assumptions on the convexity of these local losses, also on the gradient and the learning rate and more. Delving more into the decentralized learning literature, in the literature there have been two main families for decentralized algorithms, the gossip algorithms and the random walk algorithm. Today in our talk, we're focusing on the random walk algorithms. However, I will give you a hint on how the gossip algorithm work before getting into that. So in the gossip algorithm, each node in the network acts as a parameter server. Each node in the network would be learning a local model. And in order to do that, at every round of the training, all nodes update their local models and share these local models over the network. So for example, I have n nodes in the network, so I would be the computation complexity per round would be of the order of n, and also the communication complexity per round would be of the order of the number of edges in the network, because all the communication links would be activated. And the training will end once we reach a consensus state, meaning all the local models become equal, and these local models are actually the global model that we were seeking to learn. So as you see here, that this algorithm is heavy in terms of communication and computation, and that's why in our work, we're shifting the focus to random walk algorithms. In random walk algorithms, the learning happen, first we're gonna be learning just one model, which is the global model itself. The model will be walking on the graph. So at every round, one node will update the model, and after the update, it passes the model to its neighbor node. So it means there would be one computation per round and one communication per round, talking about the communication and the computation complexity. So how the algorithms work, it starts somewhere uniformly on the graph. So we start, for example, in this figure, we start at this node. The node performs the HGT update. Once the HGT update is performed, the model will be passed to a neighbor node that's going to be picked according to a transition matrix that define our random walk. As you see here, I'm saying that the transition matrix is P of t. So it is a function. It can change over time, what we call time heterogeneous random walk. And in this work, we will talk how we can control the transition matrix to improve the performance guarantees of the random walk algorithm. So here is some, let's talk a little bit about the previous work on random walk. So previously people, when they studied random walk learning, there has been two main lines. One line of work discussed the uniform random walk, meaning they designed the random walk in a way that they end up visiting all the nodes uniformly at random. And by that, they were imitating the standard HGT. And in their work, they focused on improving the convergence guarantee through the stochastic update. So we can see here, so in Ram et al., they suggest to use second order methods. And Yoon et al., they suggest to use advanced stochastic algorithms such as ADMM. Another line of work suggests to work on the random walk design to improve or speed up the convergence. So in Soon et al., they suggest to use non-reversible random walks. In our previous work, we propose a weighted random walk for importance sampling. And also we're going to be discussing, as we spoke before, the challenge with heterogeneity in these systems. So previous work on heterogeneity actually was mainly discussed in federated learning application, where the server is involved and which is different from our setting. So some of these methods suggest adding a regularization term to the objective to control the bias, then can a node add to the model update. And another line of work suggests, for example, in scaffold, to control the gradient itself to limit the bias. So we're going to be addressing the heterogeneity challenge in decentralized setting in the random walk, using the random walk algorithm. So here's our goal. Our goal is, as we said, to design the transition matrix to speed up the learning convergence. So at every round, the node will update the model. And after updating the model, we'll learn something about the distribution of its neighbor, and it would refine the transition probabilities and adjust its selection strategy or model passing strategy. So as we see here, so the node would be adapting to the heterogeneity of the distributed data and reducing the bias, to reduce the bias that comes from the stochastic gradient updates. As we said, in heterogeneous settings, when a node performs an update, it may bias this update towards its own data set. So the goal is to design the random walk to reduce this bias. And we're gonna be ending visiting nodes that are more informative and node that can help our optimization problem to reach its optimum faster. So So this is basically our goal. And our approach to achieve that is to use a multi-arm bandit sampling framework. So our strategy is a combination of exploration and exploitation. We would be exploring the distributed data, and we're gonna be using what we have explored to adjust our sampling or our transition strategy. So along the walk, what the node's gonna have, it's gonna observe the gradients updates and learn something from these updates about the distributed data. And using these updates, we're gonna be refining or tuning our transition probabilities. And the goal is to reduce the high variance in the stochastic gradient that comes from the heterogeneity of the distributed data. So just reminding you about a general multi-arm bandit framework before moving on. So what we have in a multi-arm bandit problem, so it's a game, and the player in this game is selecting an arm, as you see here in the figure, this is the octopus, is gonna be selecting one arm at every round. Each arm has a hidden cost that we don't know. And once selecting this arm, the octopus gonna observe a sample from that cost. And using what we observe, he gonna learn something about the cost distribution of the arm, and he gonna adjust his future selection strategy. So for example, we're gonna playing this game for T rounds, and the octopus goal is to minimize the accumulated cost over the rounds. At the beginning, the octopus won't know anything, so he will be in an exploration phase, and his selection strategy would be a uniform. He will uniformly select one of the arms. With time, when he learns more and more about the cost of selecting the arms, he will adjust his sampling probability and favor more the arm with less costs. So as we see here, we can define what we call the regret in the multi-arm bandit literature, which is the cost that I end up getting from my, or the octopus end up getting from his selection strategy versus the minimal cost if we know everything before starting the training, if we knew all these costs before the starting of the training. So if you knew this cost at the beginning, we would be able to design the optimal sampling strategy from the beginning, but this is not available. So we're gonna learn this over the rounds of the game. So here's again, so on our approach, so in our approach, so we're saying that we're gonna model the nodes of the graph as arms, and selecting an arm for us is selecting the next node to activate in the random walk. And the cost that we're defining, we're saying that the cost for us is gonna be the variance of the norm of the local stochastic gradient. And our goal is to minimize this variance. So it's gonna compete with the minimum variance if we knew everything about the distributed data a priori, and so we can get this minimal variance by designing an optimal sampling strategy. So we're gonna try to approach this optimal sampling strategy and then approaching the minimal variance. And as we see here, the variance is a main component in the convergence rate. So here specifically, it's the second node, the second order moment of the node. And the regret would be defined as the gap to the minimum cost. And from here, we can derive that what we need to observe at every round or at every iteration after performing the update at the node, we need to observe the cost that is the norm of the gradient that's been used for the update. So you can see here that we don't need to compute any new quantity. So the update gonna be the gradient gonna be computed for the update, and it's enough to compute to use the norm to incorporate it in the cost and use it to tune our transition probabilities. However, there is one main variation between the multi-arm bandit problem and our problem, which is for us, not all the arms are available at every iteration. As you see when walking on the graph, only the neighbor nodes are available. So we're gonna be using a variation of multi-arm bandit that we call the sleeping multi-arm bandit. And sleeping multi-arm bandit means only a subset of arms is available at a given round. This subset of arms for us is the neighbor nodes and the node itself, since we are allowing self loops. And not just that, this availability schedule or this slipping schedule is actually dependent and dictated by the graph structure. It means like nodes that are neighbored, they're gonna be available together. There is no other option. So this dependency gonna be modeled through the availability. So we're gonna assume dependent availability. And previous work on the literature in sleeping multi-arm bandit has discussed all these assumptions on dependent availability and non-independent availability and even non-stochastic availability. And you can see that the regret is always sublinear with time in all cases, and depends on the number of arms that we have in the graph, or the number of nodes for us that we have in the graph. And so the algorithm gonna works as follows. So first of all, we have what we call the exploration rate, and this exploration rate gonna be decaying over time, since we're gonna be starting with a high rate of exploration, and with time we're gonna shift to more exploitation. And at the beginning we start with importance weights that are uniform over the nodes, since we don't know anything about the local data sets. And we're gonna use this importance weights to design our transition probabilities. Once we decide our transition probabilities and we pick the node to activate, the active node will update the model, will compute the gradient and perform the SGD update. And as we said, we're gonna use this gradient computation to learn about the cost of using this ARM local data set or this node local data set. And we're gonna be incorporating this cost to tune the importance weight that we are estimating for the node. So we can see that we're doing this tuning at the last step. And we're gonna repeat, we're gonna use the new importance weight to redesign the transition matrix and select the next node.
Ghadir, can you wrap up in 1 minute, please?
Sure, I'm done. So basically here we develop the convergence guarantees, and we see that we are approaching the minimal variance within a constant. And this would sure depend on the graph structure, depends on other assumption on the convexity and the gradient. And last, we have simulated this algorithm versus other random walk designs, and we can see that the bandit random walk outperform other designs. And one last thing that I want to show, that also we simulated this algorithm for different level of heterogeneity on the graph, and you can see how consistent the bandit algorithm is consistent and outperforming the uniform random walk. And yeah, basically one last thing, maybe I should show that for different even level of density, like for example, here we simulated the Erdo training graph with different probability of connectivity. And also with a different level of connectivity, we see that the bandit random walk is outperforming the baseline algorithm. So basically, that's all. Thank you.
Thanks a lot, Ghadir. I think I'll give some time for a very quick questions, and then Mary will take over chairing the session. Are there any questions? Okay, thanks a lot, Ghadir.